Hello, this is Mike Kolbeck. I'm a student in Neural Networks and Deep Learning at DePaul University, and today I will be kind of walking through the code changes that I've made to Network 2. So I'll kind of start with kind of the major structural changes, and then we'll move into a couple of the specifics. So when this whole network is created, it kind of starts off on using this kind of class network. So we've added a couple things here. Now we have these modular costs, hidden activation functions, and output activation functions. So let's take a look at where that's actually changed so we can see where that's all done. So to kind of add in some conditional behavior here, so there's certain pairings of certain activation and cost functions that we want to kind of make sure don't mix. So this code here will kind of make sure to select certain ones that we don't end up with, like hyperbola tangent paired with some other activation, some other function that we don't want it paired with. Now, other than these sort of hard set inputs, it will take whatever the hidden activation, output activation, regularization, and cost classes that are passed to it from one of these sort of declarations here. So we'll kind of say, hey, use relative, use reticulated units, or use softmax, and it will go and actually use these classes that are up here at the top. So quadratic, it kind of came with cross entropy. I've implemented here. So I gotta sort of thank the student on Piazza who recommended this np.divide syntax, because that really makes it a whole lot easier to divide this by this onto a default array of zeros only when meeting these conditions. So that's a lot more effective, and I think that's what mostly works. I have log likelihood here too, which is a little bit shakier to kind of get around the sort of like log of 0 is infinity trick. I'm just trying to filter out zeros here. I don't know if it's necessarily the best way of doing it or not. And for the derivative here, I have -1 divided by a, which is the derivative of negative log. So that is, again, using that divide functionality too. So those are the cost functions, and those are just sort of these plug-and-play classes that can be instantiated with the network when you create it. We also have the activation function, so sigmoid kind of came with it. Softmax, again, uses np.divide syntax, saved a lot of trouble compared to my original implementation here. We had the derivative kind of by default. Tangent was kind of interesting, so I kind of used the function that was given in the slides, and then I kind of self-referenced that because the derivative is just 1 minus hyperbolic tangent squared. So reticulated linear units. So this one's pretty straightforward. It's just taking the maximum of either z or 0. And then the derivative of that is either 1 or 0, depending on whether you're above or below 0. So these ones are pretty straightforward. But so we have these cost functions, we have these activation functions. So there's a few more things that had to happen. So down here on line 300. So we had to actually set things up to use the correct output functions or activation functions. So by default, it was just using the self.hidden function. I've also added some conditional logic here that if it's the last layer, use the output function. As well, we also implemented regularization and backpropagation. So regularization here, when it kind of comes in, it will take one of these classes shown above here as an input. And we've got L1 regularization, L2 regularization. And what I've done here is I've found the two places that regularization is used, and I've abstracted those out into functions. Then depending on which version of the function, kind of like command pattern style, you'll get one of the two other behaviors. So the get regularization adjustment is kind of like the larger, like how much it's adjusting the total deltas, and then the get weight update regularization is kind of used. I'll show you where that's actually used. So on 397, we have, instead of having the weight, actually setting the weights to kind of a hard-coded value like we have here, we'll use whichever regularization function it is, and we'll get weight update regularization and pass it all the necessary parameters. So that will kind of be used for actually setting the sort of updating the weights. And then we also, though, down on 502, need to use that for adjusting the cost. So I've kind of taken those into separate methods that you can see up here, where we will get either the weight update or the cost update regularization. So that's just kind of self-contained here, 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 and here. Then we have backpropagation. I've implemented on line 422. So I've kind of gone back and forth on a couple places of where to actually put this. So I decided to put it in back propagation. So it's used once per mini batch, so once per epoch. So throughout this batch, this will be kind of this dropout mask, and then it will multiply all those activations, kind of as given on the assignment source sheet, by this array, and that will effectively knock out those elements in the array of activations, so that they will no longer be used, kind of either feeding forward or feeding backward. And we have this normalization over here, where we kind of divide everything by this retention rate. This retention rate comes from a function that I put towards the beginning of the class, right after init. So we have the set dropout. Basically, it sets the dropout, and then it takes whatever the dropout that is passed, and it just subtracts that from 1 to get the actual dropout. So when we actually run a couple of these, I'll sort of show how it works. So we're loading the network, we're selecting a hidden and then an output function, a cost function, we're setting a dropout, and then down here we have like the regularization information. And let's look at what this does. And this runs. Doesn't necessarily generate the prettiest of behavior, and I'm still pretty worried about getting these like negative costs from log likelihood, but overall everything does seem to work pretty well. So thank you. If you have any questions, hit me up at michael.b.kolbeck@gmail.com. Thanks.